Okay, let's dive right into this. So you've spent hours, maybe even days, preparing your dataset, you've carefully selected your architecture, and finally, you hit that glorious train button on your fine-tuning job. You can hear the fan on your GPU spinning up, but what's actually happening under the hood? I mean, are we literally just crossing our fingers and hoping for the best here? Because honestly, it's incredibly easy to just start a training run these days. But evaluating whether that training is actually successful, figuring out if your model is truly learning rather than just memorizing data or flat out hallucinating, that requires looking much, much closer at the model's vital signs. Think about it. You wouldn't trust a doctor who doesn't even check your pulse, right? Well, you definitely shouldn't trust an AI training run without checking its vitals. So in this explainer, we're going to completely master the art of reading learning curves. These visual graphs of your model's performance metrics over time, they are absolutely crucial. They're our ultimate diagnostic tool. They let us monitor the health of our models during the training process, helping us catch potentially fatal issues long before they totally ruin our final results. Here is how we're going to break this down. First, the vital signs of AI. Second, the anatomy of healthy curves. Then we'll diagnose overfitting, followed by diagnosing underfitting. Fifth, taming erratic training behavior. And finally, your exact next steps. All right, let's kick things off with Section 1, the vital signs of AI. The very first vital sign you need to know is the loss curve. Basically, think of loss as a measure of how wrong your model is. This curve literally just shows you how that error changes over your training steps, or epochs. Now, when you first start training, this number is going to be really high because the model is essentially just making random guesses. Its predictions are terrible. But kind of like a fever breaking, you really want to see this curve smoothly decrease over time until it finally stabilizes at a nice, low, healthy value. Okay, so our second vital sign is the accuracy curve. While loss is all about how wrong the model is, accuracy is just a super straightforward percentage of its correct predictions. And naturally, you want this health metric to go up. It's going to start out low when the model is naive, but it should generally improve over those training steps as the model successfully learns all the underlying patterns hiding in your data. Now, take a look at this. What's really fascinating here is the distinct visual contrast between how these two specific curves behave in practice. If you're looking at your dashboard, a healthy loss curve usually looks continuous and pretty smooth. It just glides downwards. But the accuracy curve, it looks entirely different. It's discrete. It actually looks a lot like a staircase. It's super steppy. And this quote right here brilliantly illustrates exactly why accuracy has those weird plateaus. Let's imagine you're training a basic binary classifier to tell cats from dogs, okay? A cat is 0, a dog is 1. If your model looks at a picture of a dog and predicts 0.3, well, it's wrong. And the loss is calculated based on that exact 0.3. Now, if on the very next try it predicts 0.4, it's still wrong, right? Because it hasn't crossed the 0.5 threshold yet. Your loss curve will smoothly go down because, hey, 0.4 is closer to 1, so the model is getting more confident. But the accuracy? That line remains totally flat until the prediction suddenly crosses that threshold and actually becomes a correct classification. And that is exactly why accuracy jumps up in those discrete little steps. Moving right along to Section 2, Anatomy of Healthy Learning Curves. So a well-behaved, perfectly healthy training run is going to show a really steady, smooth decline in both your training loss and your validation loss. What you're looking for is a very small gap between how the model performs on the training data it's studying and how it handles the validation data it has literally never seen before. Finally, both of these curves should eventually level off. This leveling off has a name. It's called convergence. And convergence is the ultimate goal here. It's the green light signaling that your model has effectively learned the patterns and is finally ready for the real world. Let's get into the tricky stuff. Section 3, diagnosing overfitting. Because unfortunately, models get sick. They definitely don't always converge perfectly. The first illness we're diagnosing today is a super common one, overfitting. This happens when the model basically just memorizes the training data perfectly, but then completely fails to generalize to any new, unseen data. So let's test your diagnostic skills for a second. If you're staring at your dashboard and you see your training loss beautifully continuing to go down, but suddenly your validation loss stops decreasing and actually starts creeping back up, what is your diagnosis? Well, the absolutely crucial point here is that this exact divergence is the classic textbook symptom of overfitting. The model is getting better and better at the training test by essentially cheating and memorizing the answers, but it's completely losing its ability to handle the validation test. You're also going to see a massive widening gap between your training accuracy and your validation accuracy. If you spot these symptoms, here is your exact prescription. First off, implement early stopping. If that validation performance hasn't improved for, say, 3 consecutive epochs, just pull the plug and stop the training. You can also add regularization techniques, things like dropout or weight decay, which actively penalize the model for getting too overly complex. Also, try data augmentation to pump up the diversity of your training set, or honestly, just use a smaller model with fewer parameters altogether. All right, on to section 4, diagnosing underfitting. Let's look at the exact opposite problem now. Underfitting happens when your model is just way too simple to actually capture the underlying patterns in your dataset. And I gotta say, the symptoms here are pretty depressing to watch live on a dashboard. Both your training and validation loss just remain stubbornly high. They won't budge. The model's performance plateaus almost immediately after you start training. If your training accuracy is sitting way lower than you'd expect for the task, well, the model simply lacks the brain capacity to learn what you're trying to teach it. So to treat underfitting, you literally need to give the model more brain power. Increase that model capacity by using a much larger architecture or just more parameters. Sometimes, though, the model just needs a little more time, so try training it for more epochs. You might also need to tweak your learning rate or, and this is a big one, take a really hard look at your data pre-processing. Make absolutely sure you aren't accidentally feeding the model pure garbage data that's mathematically impossible to learn from. Section 5, taming erratic training behavior. Now, this third element is probably the most anxiety-inducing one to watch in real time. It's almost like an irregular heartbeat. Trust me, you'll know it when you see it. When both your training and validation curves look like violent, chaotic zigzags rather than nice, smooth lines, your model is really struggling. This means the model is experiencing high variance. It's most likely overshooting the optimal parameters entirely with every single step, or it's just aggressively trying to learn from random noise in your data instead of the actual true patterns. The best, absolute, most immediate approach to stabilize this erratic heartbeat is to just lower your learning rate. Reduce that step size so the model is forced to take smaller, much more careful steps toward optimization. You should definitely also increase the batch size, which gives the model more stable, averaged out gradients. And finally, implementing gradient clipping can act as a great safety net to prevent those massive, exploding gradients from throwing your model completely off a cliff. And finally, section 6, your next steps. Okay, now that you essentially have your honorary medical degree in AI model diagnostics, let's summarize exactly how to apply all of this to your own real-world fine-tuning projects. Here is your master cheat sheet. Definitely keep this one handy. When validation loss rises while training loss falls, you're overfitting. Hit it right away with early stopping. When both losses stay stubbornly high, you're underfitting. Give that model some more capacity. And when the curves look like crazy wild zigzags, it's erratic. Immediately lower that learning rate. Oh, and I highly recommend using visualization tools like weights and biases to track these metrics live right side by side. It makes it so easy to instantly diagnose and prescribe a fix mid-flight. Because look, practice really does make perfect in this field. The next time you fire up a training loop, don't just hit run, walk away, and grab a coffee. Sit there, watch those curves, draw themselves in real time, and really analyze them. Push your hyperparameters around a bit. Intentionally set your learning rate way too high or make your model way too small, and just watch how these vital signs react. Because once you actually achieve stable vital signs, that is when the real fun begins. You start asking yourself just how absolutely optimized can I make this model? So what hidden performance are you going to unlock on your very next run?